Hello, my name is Todd Rothman. Welcome back to Organic Chemistry 1. In this video, we're going to go over the conformations of cyclohexane. Now, cyclohexane is the molecule that we use as reference, but the things that we're going to learn here in cyclohexane really apply to other systems as well. But we just need, something, and cyclohexane being the most stable is the best place to begin. It's a good one to reference. So let's get started. Let's talk about the energy diagram and the comparison of the different conformations. Now, cyclohexane, as I mentioned, it's the best one to start learning from because it's the most stable. And what we're going to see is that, remember, cyclohexane is a 6-membered ring system. And what I want to point out at this very moment is I want you to track the end pieces of a cyclohexane. So the bottom left and the top right in this drawing. Now, if I was to take the cyclohexane and push up the blue side and pull down the red side, so it's actually blue side up, red side down. If I was to do that, then I would get this right here. And all I did was interconvert what's pointing up and what's pointing down. So the blue goes up, the red goes down, then the red goes up and the blue goes down. And it just keeps going up and down, up and down. And these are the two conformers that we're focusing in on. So remember, conformer is a snapshot in time, and at any moment you'll catch the cyclohexane in some path going from blue up, red down, to red up and blue down. And so you'll see it just going back and forth. Okay, that's what these molecules do. Ring systems do not rotate. Because of the ring, it restricts rotation. But it does go in this form here. Okay, now, and so by the way, so this is known as a chair conformation. These are chairs, and so I'm showing you an illustration of me sitting on a chair, drinking some rum on a beach. And I do have to admit, I was a bit thinner back then. I'm not that thin anymore. But this is an old picture of me. So anyway, so you could see here how a chair, why we call it the chair conformation, right? It's all because it looks like a chair that you can sit on. So let's go ahead and talk about these energy changes. So I just gave you the big picture. I told you how to go from one chair to another chair. So we can go back and forth, chair to chair. But there are things that happen in between, right? So as I'm showing you, even with my hands, we could stop at any moment. And where will I be when my hands are moving up and down like that, right? And that's what we're going to see here. So it turns out that these are the different conformers that we need to know about. Remember how with an alkane, we have eclipsed and staggered. And we went through 60-degree changes to go from eclipsed to staggered over and over again, right? Well, these are the changes. These are the pictures in time, the snapshots. Okay, so here's the first conformer, a chair. Then you have what's known as a half chair. Now think about what we're doing here. All we're doing is we're pulling this up, and you get to this flat piece here. So once you pull it up to become flat, notice how it shoots up in energy. Remember, this is increase in energy. So we'll see why in the next page, why that just increased in energy. But for now, let's just take a look. Now, what happens next is it twists. So it goes to a twist, which is over here, what's known as a twist boat. It's the same thing, twist boat or twist. And that brings it down in energy. And we'll see why in a moment as well. But then what happens is you could think of the blue and the red are now on the same side. These two carbons are either up or down. It depends if you flip the molecule, right? But if they're both pointing up, this is known as a boat, and you could see it looks like a boat, right? So I could be, right here, like in Dexter, driving my boat, throwing bodies over. Well, I wouldn't do that, I'm joking. But, there's the boat. Okay, so we're driving our boat, and now what? Now we go through another twist. And so with the twist, we go back down in energy. So notice, I want you to keep in mind the relative energy positions. This being the most stable, this up here, the half chair, being the highest in energy. Twist, lower. Boat is a little higher than twist, but not as high as the half chair. So get the idea. So it goes through another twist, and then it goes through another half chair. So now, instead of this side being up, the blue is up, and the red is now flat, going straight. And then eventually, the red's going to drop down now, right? So now this is going to drop down, and we get to that other chair. So these are the conformations of cyclohexane. These are the ones that we have to be familiar with. Now, truth be told, we focus almost exclusively on the chair because the chair is the most stable. but we are right now going to touch a little bit on the other ones. But throughout the whole semester, you might hear boat once throughout the rest of the year, or twice, maybe I can think of when. But chair, you talk about a lot. So we'll learn about that in carbohydrate chemistry. We'll learn about that throughout the whole semester in different areas, okay? So, like for example, we're going to learn about substitution and elimination reactions, and we'll learn about chairs again back then. So, let's get an idea of what these energy differences are. What is the potential energy of the systems? Why is half chair so high, twist not as high as boat, and so on? Well, first off, let's talk about chair, the most stable. Chair has no angle strain. It has, now again, remember, everyone has steric. Steric strain is universal. Anytime electron clouds are coming together, they're going to have steric interaction. They're going to have repulsion. So every system has that, but it has no angle. It has no torsional. Remember, torsional means eclipse, and there's no eclipsing in a cyclohexane. Cyclohexanes are super stable. I have a molecule here. I don't know if this is going to come out very well. This is a cyclohexane, right? See how it's 6? Now, if I turn it on its side and I make it into its chair, look what I just did. I just twisted this up and pushed this one down. This is pointing down. This is pointing up. Now, look at it from the side point of view. Look at that. It's completely staggered, right? This would be eclipse. If it was flat, it would be like that eclipse, but it's not. It's staggered. So every carbon, every 2 carbons in this ring system is staggered. And so everything has freedom. The red has nothing in front of it. This is super important. Every bond, I don't have, if I put all this together, it would fall apart. But if you look at any 2, it's always staggered. So that's the thing about the 6-membered ring. In the chair form, everything's staggered. That is the key. Okay? And so because of it being staggered, that means that it has no torsional strain. Okay. Now, it has what's known as axial equatorial. I want to point out that any 3-dimensional ring will have this. What do I mean? Cyclopropane is stuck. It's flat. It has got all torsional strain. It is completely flat, 2-dimensional, which means it has no axial equatorial bonds. But once you start pushing things off of planes, once you start making it 3-dimensional, like cyclobutane looks like the Star Trek symbol. And so that means that it has some 3-dimensionality to it. So it has axial equatorial bonds. Cyclopentane, cyclohexane, and so on. They all are going up. They have these 3-dimensional characteristics, which means that they have 2 bond types known as axial and equatorial. We'll learn about them soon. But for now, I just want to point out what that means. Now, look at the boat. The boat, it turns out that 4 of its carbons, okay, I'll do it in green. This carbon, this carbon, and that carbon, when you go into the boat form, they become eclipse. So this here and this here, they have torsional strain. So that they are becoming eclipse. So as you interconvert, eclipse occurs. Okay, torsional strain occurs. Now, the other thing is these are known as flag pole H's or hydrogens. Now, what happens is when you have the boat, the H's start to come into each other's space. And so the boat pushes the H's towards each other. And if it's, of course, bigger systems, like let's say bigger branches like methyls or bromo or tert-butyls, massive amounts of strain, right? So as this becomes bigger, this electron cloud, then clearly you're going to have more and more strain. And that's the idea here. So that one here has strain, but it has both gauche interaction that you would expect. This right here is a gauche, an extra gauche. In addition to its regular gauche that everybody has, this is extra gauche that not everyone has. Plus, it's got torsional strain. Very important. It's got 4 carbons that are pointing exactly down below or up above, and they're going to be torsional to each other. They're going to have that eclipse issue. All right. Now, when you go into a half chair, remember, half chair is the highest in energy. When you have a half chair, when we look at the half chair, the problem here is that this carbon and this carbon and this carbon and that carbon and this carbon and even this carbon